Alright folks, let's get started with the episode 3 for this LLM from scratch series. And in this episode what we will do is we will build the core components of LLM architecture, and we will do it in a step-by-step manner. I will explain you what are the different steps of building LLM architecture, which is mainly a decoder based architecture, and then we will try to implement that in the code. First of all, this is the famous transformer architecture, which has encoder decoder based architecture, which actually got famous from the attention is all you need paper, where we have two components. So one of them is the encoder, so this part is the encoder side, and then we also have a decoder part. So this encoder side and the decoder side, combining these two, the transformer architecture initially got started. Then with the advent of like generative AI and large language model, mainly we focused on this decoder side of the LLM, right? So what we will build in this episode is we will build a decoder based LLM architecture where we will only implement the decoder side, and there are a few modifications which we will do in this architecture. First of all, like here we have this cross attention. So this cross attention we will be not be implementing in this. So this part we will eliminate. So all this part we will eliminate, and we will simply implement a masked multi-head attention instead of a cross attention. So that we will eliminate, and then we will like build this whole architecture. Before going to the coding part, so I just wanted to show you how the decoder based architecture looks like, which we will actually implement. So you can see like we have the input, then the input goes through the embedding, then we add the positional encoding, and so then we have the decoder based LLM architecture, right, which consists of attention block, then the add-Norm layer, and we have the feedforward layer, and again add-Norm layer which we have, and then finally we have the linear head, which will predict the logits based on the vocabulary size, right? The nomenclatures which I wanted to go through first before going into the code implementation. So the first one is a batch size. So we have gone through this, but as we have seen in the last video in this series, we create a batch with a shape of like B cross T. So this B is nothing but the batch size. That means the number of rows that we send to the model to get the prediction. Then we calculate the loss, and then we do the back propagation to update the model parameters, right? So the number of records that we send as a batch is nothing but the batch size, right? So here we can see like the batch size is 4. So the B value is equals to 4. So we have the vocab size. So this vocab size is nothing but that depends on the vocabulary you are building on. So if you are using a byte pair encoding methodology to build the vocabulary, so the vocab size is around 50k if I am not wrong, which also the GPT-2 based architecture, if you follow, then the vocab size is around 50k. So this vocab size will be actually very important when we will make the final prediction using the linear layer. The output from the linear layer will be the equal to the vocab size. Then we will sample the highest probability, and then we will come up with a one token for as a prediction, right? So that's what the vocab size is. Then we have this concept of time dimension, what we can also call as context length or the sequence length or the block size, right? So which we also denote as T, right? So this is the maximum amount of token the LLM can consume at a time, right? So you can see here we have like 6 tokens which we have for every rows in this record, right? So 1, 2, 3, 4, 5, and 6. Right? Once the new LLM gets released, there is a parameter which tells you like what is the context length, right? So for modern LLM, it's like 128k. The value is around 128k. So that means like 128k number of tokens you can pass to the LLM at once, and then you will get the prediction using the LLM. So if you send a larger context or sequence which is greater than this context length, then the LLM generally throws an error, right? So we will see when we implement the generation phase code, we will see like how we can tackle this the time dimension or the context length, and that we will see during the implementation. So just to just to be clear, so all these things remains are same, like the time dimension, context length, sequence length, or the block size. So you can call it any of these terminologies, but that means the same thing, and we denote it generally using this T, right? So then the other thing which I wanted to talk about is the N embedding, or the embedding dim, or the channel length, right? So we can call it with a nomenclature of N, or sometimes people call it as C, which is they also call as channel length, and the other thing they also call it as D, right? So this is this is one token, right? So this is one token. Once you pass through this to the embedding uh, phase, then it will create a stretched out vector, right? So this will be represented with a numerical value with a long vector, which can be a shape of n embedding, right? So if you remember, like we will also do it in the code itself. So we will start with an embedding of equals to 384, right? So there would be like 384 values in this stretched out vector for this single token, right? So this is what we actually call as an embedding. So that is nothing but the embedding dimension shape, right? Pass through this input to the embedding model, then we will get output which will be equals to as B cross T cross D, right? And D is nothing but the ndim, or the embedding dimension shape, right? So this is actually an important concept which I wanted to tell you at first to get rid of the confusions which you might have, right? We'll also talk about is the token generation process. Token generation process, if I just to draw you with an example and try to explain you the concept. So at first we will have a sequence. So let the sequence be like LLM from scratch, right? So this is a sequence, the input sequence which we have. Then what we do is we have a model trained which we have as LLM. Do is we will pass this input token to the LLM. So how this actually work is, so this sentence will be using the encoding method. So you will add a start of sentence token, and then at first you will send this start of sentence token, and that will pass through the LLM, and you expect if the model is well trained, then it will generate LLM as the next token. Then that next token will be appended to the input, right? So this will be flown back from here to here, and now you will send this two tokens together to the LLM, right? And you will expect that the LLM will generate LLM from, right? And then again you will concatenate this token here, and that you will send to the LLM to get the final output, which is like scratch, right? So actually this won't be the final output. Then again you will add this scratch to this input. You will extend the context length, and that you will send to the LLM, and you will expect that the LLM will produce a end of sentence token, the EOS, right? So that will terminate the process of generation, and it will give you the output to the user, right? So this depends, like you can also bring in a parameter which is like max output token. So that also you can define as a parameter. So you can define a value like 500, right? So this process of generation will keep on going till you reach the 500 token in the output, right? So the main part of this process which I wanted to explain is that you will only be bothered at the output for the last token, right? So which we will fetch the last token. So every time it will keep on generating the full sentence, but you will only pick up the last token from this output, and that we will append to this input, right? And rest of the tokens we are not bothered, because that has been already taken and appended to the context what we are sending to the LLM, right? So that is one thing which we will also see in terms of code, that we will only be bothered about the last token, and that we will capture and we will add back to the context, and then we will send that to the LLM for the next token generation. Now let's go through very quickly how the masked multi-head attention works using certain visualization which I have created for you. So in case of self-attention, right? So we generally have this encoder decoder architecture when we are like doing a machine translation task. So when we are like passing one language to the encoder side, so this can be a language called Bengali, and that we are passing to the encoder side. Each of this one by one we are passing each of the tokens of a particular sentence, and then we are like kind of calculating the hidden states like h1, h2, h3 and h4. Then h4 once we generate that will kind of act as a context vector, and that we will pass to the decoder to generate the further tokens in a different language. So that language can be English, right? So the problem with this sequence to sequence model is we are expecting a lot from this context vector, right? So we are expecting this context vector to like incorporate all the hidden states which are here, right? And with that hidden states incorporated in the context vector, then we are translating it to a different language. That can create a lot of problem, but what I have talked about in my deep learning with PyTorch playlist, so you can go ahead and look into those videos. Now to tackle this, what we can do is we can make this a few changes in this architecture. So what we can do is, instead of only depending on the h4, we will also incorporate the other states, or we will also make available all the other states from this encoder side for the context vector, right? So, and along with that we will also calculate attention score. So if for an example, like if y2, when we are translating a particular language to another language, and for a particular token like for y2, if that has more emphasis on a hidden state which is associated with h3, right? So the attention score will be higher for this h3 for y2, right? So each of these individual states, each of these individual tokens will get a context vector like c1, c2, c3 and c4, right? So all this will get an individual context vector, and then with that it can like using the attention score, it can like put more emphasis on certain parts of the input sequence, and with that the translation will happen in a much better way, right? So this is what a basic concept of self attention is in case of encoder decoder architecture, right? Now let's try to visualize this this basic form. So what we generally have is we have this xi, which is my current input, and for that we are kind of calculating the dot products between xi to the all other input tokens, which are like x1, x2, x3 and xt. Then once we calculate the dot product, so this dot product is kind of gives you the what is the similarity between these two tokens, and once we have those dot products, then we can normalize using a softmax, and after that we can calculate more context aware embedding vector for xi, right? So this is like using this j equals to 1 summation to t multiplied by aij with xj, we can calculate the ai. So that is kind of a more context aware embedding vector for the xi, right? So this is a very basic form of self attention, where we are kind of, first of all we are doing a dot product, then normalizing using a softmax, and then we are calculating the final embedding vector, which is more context aware, right? So here you can see there is no learnable parameters in this approach, right? So what we can do is we can now bring in certain learnable parameters through which while doing the back propagation in this neural network, it will also learn those parameters during the back propagation. So we have 3 trainable matrices which are like wq, wk and wv, right? So this 3 trainable matrices are multiplied with the input sequence to get the query key and value, right? So we get the query vector, or the query vector by multiplying wq with xi, then we have the key vector and also the value vector, right? So what we are doing is we are passing the x, and x is getting multiplied with wq, wk and wv, and we are getting the corresponding qkv, right? So this query key and value, this concept came from the attention is all you need paper, and that is kind of the learnable parameter which we have introduced in this architecture, right? So once we have these matrices, what we do is we do this operation, right? So at first we multiply q with k transpose. Then to minimize the variation of this, the variance of this multiplication of q multiplied by k transpose, if we don't like divide this with the root of the dimension of k, then we will get a huge variance of this multiplication, right? So just to minimize the variance of this multiplication, we are like dividing this qk transpose by the square root of the dimension of k, right? Here, just for an illustrative purpose, I am taking an example like this is my input sequence, which is like attention is all you need. So the length of this sequence is 5, right? Then we have this k, which is the embedding size, right? So embedding size is like for each token, right? So if I talk about this attention, it will be represented with a long stretched out vector, and this shape of this is k, which is usually in attention all you need paper is 512, right? So with that, what we will do is, let me first clear this. Okay, so what we will do is we introduce the q matrix, which is n cross k, and then we multiply with like k transpose, which like after doing the transpose the shape is k cross n. Now we are multiplying n cross k with k cross n. So, and then we are dividing by the square root of k, right? Just as I mentioned, this is to reduce the variance of this dot product, right? Then what we are doing is we are doing a softmax on top of this whole operation, and we are getting an output. This output is nothing but a attention based matrix, and that the shape of that is n cross n, right? So this is what we call as attention based matrix, where each part of the token is kind of have a attention score associated with a different the other tokens that are present in the input sequence. N is nothing but the sequence length, right? So if I just take this example, so we have this n cross k, which is our q. So this is like 5 cross 512, right? So as I mentioned, like inattention is all you need in paper, this k is equals to 512. So for this example, the shape of q is 5 cross 512. Then we are multiplying with, like after doing the transpose, we are multiplying with a shape of 5 cross 12 cross 5, and then we are like dividing it by the square root of k, and then we are taking the softmax, and what we are getting as in the output is 5 cross 5 attention based matrix, right? So n is nothing but the sequence length which we are mentioning here for this example. So after that, what we are doing is we have done the first part, like doing the softmax operation on this after doing the dot product. Then we need to multiply this with the value vector, right? So we got the attention matrix, which is like this n cross n matrix, and that we will multiply with v. So v is nothing but a shape of n cross k. So we are multiplying n cross n with n cross k. So the output what we will get is n cross k, right? So this what we call as embedding vector, and this embedding vector is much more context aware. So we are calling this as attention based embedding, right? About what is multi-head attention, right? So we talked about self attention, and now let's talk about what is multi-head attention, right? So in the multi-head attention, the concept remains the same, just that we are having multiple heads which we will calculate using the formula that we have already talked about using the attention mechanism, right? So we have our input. That input is get multiplied with the different learnable matrices which are like wq, wk and wv, and we get the corresponding query key and value vectors. So once we have that, what we will do is we will divide each of these matrices, like the q will be divided into 3 matrices like q1, q2 and q3, right? So we are kind of introducing this multi-head by dividing the q to multiple heads, right? So similarly we will do that operation for the k matrix and also for the v matrix. So we have corresponding k1, k2, k3 and also the v1, v2 and v3 for q1, q2 and q3. Now we do this attention operation. Using this formula, we will calculate each of these heads, which are like h1, h2 and h3. using this same formula which I already talked about in the last few minutes. And after that, what we will do is we will concatenate each of these heads like H1, H2 and H3, and that gets multiplied with a output matrix which is WO, and we get the multi-head attention, right? So in one head it may be picking up certain characteristics of the input sequence, and using multiple heads we assume that it will pick up the other qualities of the input sequence, and it will be more diverse in terms of calculating the attention of the for different characteristics of the input sequence, right? So once we have this multi-head attention, then let's talk about the masked multi-head attention, right? So why we need first of all the masking, right? So in case of encoder side, right, so this is the encoder side example. Your any of the tokens, right, if I talk about this all token, right, so that token can look into the past tokens, the previous tokens, and also it can look into the future tokens, right? So this is what it can happen in case of encoder side, because encoder side we are mainly generating the embeddings, and embeddings can look at the past behavior of the input sentence or the input sequence, and also it can look ahead for the future tokens or the future words for the particular input sequence or input sentence, right? But it is not the case if when we are talking about the decoder side, right? So this is what we have talked about the encoder side. In decoder side, it is mainly the decoder is trained for next token prediction or the next word prediction, right? So we need to mask out the future tokens for each of these sentences, each of these tokens, right? So for attention token, it can only look at till this part, and after that it is all zero, right? So because it cannot look ahead what are the tokens that are coming in the future. If it looks into the future tokens, that is kind of cheating, right? So just to avoid that, we will mask out these tokens, and we will make all the future tokens for a particular token as zero. So for like is token, it can like this values will be masked out to zero, and similarly for other tokens the future values or the future tokens are masked out to zero, right? So all this value which I am showing here, you can see like the diagonal elements are kind of highlighted because that is kind of a word is looking into itself, and those are using a self-attention mechanism. Those attention score will be much more higher, but these values are random, so I have like used random values in this matrix. So don't think like why the values are not adding up to 1, because after doing the softmax, each of these row wise elements will be summed across summed equal to 1, right? What we do in case of self attention for this decoder side is, or the causal masking we also call it, where we will make these future tokens as minus infinity, right? So once we make these future tokens as minus infinity and then apply the softmax, these values will become 0, right? So this is the concept of like masked multi-head attention, and this we will do for all the other heads. So this is for one head, and that operation similarly we will do for the all the other heads that are coming from the masked multi-head attention mechanism, right? Okay, so now as we have in-depth understanding of the theory or how the multi-head attention works, now let's do the coding part. Let's go and implement this using PyTorch, right? So these are the few steps which I have noted down. Like first we will convert the text to token, then we will add the input embeddings and also the positional embedding, then we will implement the masked multi-head attention, and finally we will have the feedforward layer, and also we will do the implementation of Add+Norm layer of this decoder based LLM, right? So first of all we will download the data, then we will see whether the GPU is available or not. Based on that we will make a device variable which will make the code device agnostic. So then we will reuse the getBatch class which we have implemented in the last video in this series. And so only two things which I have added new here is I am moving the X to the device, and also I am moving the Y to the device, because that will make sure if we are using GPU the data gets moved to the device, right? So then what we will do is we will slowly, now we will do the step-by-step implementation of the decoder based architecture, and this is not a modularized code, but in the end we will make the whole code modularized. So at first we are initializing the tokenizer, then we are also getting the vocab size, and also we are mentioning that n embedding size is 384. This is just to show you how this code will work out, and then we are also mentioning that the block size is equals to 512, which is nothing but the max sequence length or the context length of the LLM, right? So now we can see that we have these values: the vocab size, the embedding dimension, and also the max sequence length, right? So we have talked about the embedding dimension, right? But if you take this example, right, if we have two sentences like Ram is behind Arun and Arun is behind Ram, right? So if you just take the embeddings of these two sentences, there those embeddings would be very much identical based on the token, because only the thing that has been different in these two sentences are the position of the Ram and Arun token, right? So they have been swapped and the meaning of the whole sentences got changed, right? So what we will do is we will add this positional information to the embedding, and then we will get the input which we will pass to the LLM architecture, right? So we will create two lookup table. So one of them is the token embedding table, which will be initialized with a shape of vocab size cross n embedding, and we will also have a positional embedding lookup table which will go till the block size, right? So we only need to consider the full sequence length that we are passing to the LLM, right? We don't need to go beyond that. So that's why the initialization in this way. So the shape is like block size cross n embedding, right? So once we do that, then we can use this get batch class, and we can get a data loader through which we can get the corresponding input and output, which you can see in the screen also. And then we can get the shape of my input, which is like b cross t. So the batch size is 4 and the max sequence length or the block size is equals to 512, right? Then we pass this x to the token embedding table, which will do a lookup of that particular sequence, and it will give you back that token embedding for that particular input sequence, right? Now the shape got changed to B cross T cross D, which is like 4 cross 512 cross 384, right? So 384 is nothing but the n embedding or the embedding dimension size, right? So then we will use this positional embedding lookup table where we will loop through till the sequence length, and we will pass the input which we got from the previous step to this to get the positional embedding, right? And then we can like add the token embeddings and also the positional embedding to get the final embedding based representation of my input sequence, which is like B cross T cross D, which also has the embedding information and also the positional information of each of the tokens, right? So once that is done, then what we will do is we will implement the masked multi-head attention. So as you have seen in the video that we have three learnable parameters which are like WQ, WK and WV. Get the corresponding query key value by multiplying these matrices with the input sequence, and then we get the corresponding QKV matrices, right? So that's what we will do here. So at first we are looking at the shape of X, which is 4 cross 512 cross 384, and then what we will do is we will initialize this learnable parameters, right? So W query, W key and the W value, right, which will be nothing but a shape of an embedding cross the head size. So then we will pass the input sequence to through each of these learnable parameters, and we get the corresponding query key and the value matrices, right? So the shape of those three matrices you can also see, which are nothing but B cross T cross head size, right? So then once that is done, now we can start implementing the attention mechanism, where at first we will do the scale dot product, which is key qk transpose. Then we will divide that with the dimension of the k, which will make the variance less. So at first let's do this qk transpose dot product. So to do that we need to do certain transpose just to match the inner dimension. So that's what we are doing here. I'm just showing you the shape. So without the transpose, the shape is like 4 cross 512 cross 256. And now if we swap out the last two dimension, it becomes 4 cross 256 cross 512, right? So now we can do this dot product between Q and K transpose. And once that is done, then we will divide this value with the square root of the dimension of the K, right? So we are getting the dimension of the K using this, then we are just doing a square root of that, right? So this double star will do the square root, and the value is like minus 5 to the power, right? Which will do the square root of the dimension of the K, right? So then we will get this shape of 4 cross 512 cross 512, right? So at the decoder side, as we mentioned in the video, so we will mask out the future tokens. So at first we will set the upper triangular matrix to minus infinity, and then once we apply the softmax, those values will be turned to the 0, right? So we can see like we have used this masked field, which I have also discussed in the PyTorch essentials. So if you haven't gone through that video, my request would be go back to the first video in this series and get your concepts cleared, right? So once we do that, we will see that now the weight matrix has minus infinity at the upper triangular part, and then once we apply the softmax, the upper triangular part will become 0. So now we will implement the last part of calculating the attention, which we will do the dot product with the V matrix, right? So you can see we are multiplying this WEI matrix with the V matrix. So the inner dimensions are matching. So straight away we can do the dot product, and we are finally getting this shape, right? Which is B cross T cross the head size. So we are mentioning the head size equals to 256 here. Now what we will do is we will integrate everything and we will create a class out of it, and we will name that class as MaskedHead, right? So you can see like I'm mentioning the batch size equals to 32, the block size equals to 128. That means you can at max send 128 tokens at a time to the LLM to generate the next token, right? And we have the n embedding, which is a embedding dimension shape, which is 384, and also we are mentioning the dropout value is 0.2, right? So this is already, you should be familiar now. We have the corresponding w query, w key, and the w value, and also the masked register buffer which will do the masking, and also we will initialize the dropout, right? So once that is done, then we will pass the input through the query matrix, the key matrix, and the value matrix, and we will get the corresponding QKV, and then we will implement what we have discussed so far. What we will do is we will implement the multi-head attention, where we will divide each of these QKV matrices to smaller matrices, and then once we do the attention calculation, we will get different heads which are like H1, H2, and H3. So then what we will do is we will concatenate the H1, H2, and H3, and we will multiply with output weight matrix to get the multi-head attention, right? So you can see I have this multi-head attention where I am mentioning like it will take the input, like what is the number of heads you want to have, and also the head size that you want to have, right? And based on that, it will loop through those number of heads, and it will call this previously implemented masked head to do the masked multi-head attention, right? And we will wrap everything to this nn dot module list, which will be a wrapper which will create this parallel processing of this masked multi-head attention, right? So then we will have this output layer matrix, which is nothing but the WO, which is shown in this image itself. So this projection is nothing but the output WO matrix, and also we have the corresponding dropout, right? So then we are looping through each of these heads, and we are getting the corresponding head 1, head 2, and head 3 till the number of heads that we will loop through, and then we are doing the concatenation, and once the concatenation is done, then we are projecting that using the WO matrix, and we are implementing the dropout, and we are getting the final out, right? So this is what the multi-head attention implementation looks like. Now what we will do is we will implement the feedforward layer, which the shape of the first linear layer is that it will accept the n embedding as the first number of nodes. Then we will do a scale up, which will multiply 4 with the n embedding dimension, and then we will add relu. So you can also use gelu here instead of relu, which now being used with the models like llama 2 or mistral. And then we will have another linear layer, and we will have the final dropout, right? And we will also implement the forward function. Then we will integrate everything, and we will make a single decoder block where we will also do the implementation of the add and norm part, right? So you can see here at first it's accepting the parameters which are like what is your embedding dimension and also the number of heads, right? So the head size which I have shown you earlier, so this is the way to calculate. So we will divide the embedding dimension by the number of heads we want to add in the masked multi-head attention layer, right? So that will give you the head size, right? So we will use the previously created multi-head attention class, and we will pass the n head and also the head size, and we will name it as a self attention in short, which is SA, right? So once that is done, then we will implement and use the feed forward layer which we have created at the last step. Then we will implement the layer norm, and we will have two layer norms which is also shown in the architecture of this decoder based LLM, and we will name them as LN1 and LN2, right? In the forward function, what we are doing here is we are accepting the sequence input, which is nothing but X. Then we are passing the X through the self attention layer, and we are naming the output as Y, right? This is to just to create a copy, because we will also add a residual connection which will add the input to the self attention layer output and ln1 layer norm implementation, and we will get back the X, right? So then again we will do the same thing, and we will name it as Y, and we will again create the residual connection to get the final output, which is X, right? So just to show you how the residual connections are getting created, let me go back to this figure. So you can see we have this residual connections, right? So what we are doing here is we have the X here, so we are passing the X to the attention block, and we are getting the Y, and then we are propagating the X to this path, and then we will do X plus Y, and we will then implement the add a norm layer on top of this, right? And similarly we do the same thing here also, and we will create the residual connection here to this path, right? So now once all this is done, then we will do the final step, and we will build the decoder based LLM, right? So you will see that now I am mentioning the final params, which are like the block size is equals to 256, the vocab size is more than 50k. Then we will have a 6 repeated layer of masked multi-head attention. That's why the L layer value is equals to 6, and for each masked multi-head attention we will have 6 multi-heads, so that's why the n head equals to 6, embedding shape as 384, and we will have the corresponding dropout and the batch size, right? So now we will stitch together everything. So first we will implement the embedding layer, which will use the token embedding table, and also we will have the corresponding positional embedding table. Then we will have the blocks, which are nothing but the repeated blocks of the decoder blocks, so that will go till the value which we have mentioned in the n layer, right? So we have mentioned that the n layer value is 6, so we will have 6 decoder blocks in this, and then once we get that, we will implement the layer norm, and also we will have the final layer, right? So this final layer is very important here. So the shape of that would be like an embedding to the vocab size, right? So the final layer output will give you back the logits, which will have the shape of the vocab size. So then we will also do the weight initialization of the parameters which are associated with this all these layers, and finally we will have the forward function. So the forward function is nothing but an integration of everything that we have discussed so far. So we will have the embedding layer, then the positional encoding, then we will add the token embeddings to the positional embedding, and then we will pass it through the blocks that we have created previously, and we will have the layer norm, and finally we will have the language model head, right? So which will give you back the output which are like b cross t cross the vocab size, right? So then we this forward implementation also accepts the target. So if the target is none, then we will not calculate the loss, and if there is target, then what we will do is we will calculate the loss using the cross entropy loss, right? So which will accept the logits and also the targets, right? And based on that we will calculate the loss function. What we will do is we will also implement the generate function. So this generate function understanding is uh, quite essential if you want to understand how the LLM is the output is getting generated. So if I just do the visualization here, which we have also discussed at the starting of the video, so we will have the LLM, and then we will have a input sequence which are like, if I take the LLM from scratch, so then what we will do is we will pass this full size sequence to the LLM, and we will make sure that this sequence length or the length of this whole sequence should not exceed the block size, right? So you can see like that's what we are doing here. We are truncating the values which are beyond the context length or the block size. So this will make sure that we will not send any input which is beyond the block size, right? So once that is done, then we will pass it through the forward layer, which will create the logits and also the loss. So once we get the logit, so as I mentioned previously, we will only concentrate on the last generated token, right? So for an example, like if we pass this whole sequence to the LLM, so the LLM will generate every tokens, right? Starting from the very beginning. So it will generate this LLM from scratch implementation, right? So this is the new token which got generated. So now our point of interest is only this new token, right? Which is the last token, right? So what we will do is we will extract this last token and we will add that to the input sequence, right? Here, right? So which will do the concatenation of this implementation token here, and then again we will send this to the LLM, right? And so every time we will only uh, get bother about the last token, and that we will concatenate to the input sequence, and that we will send to the LLM for the next token generation, right? And this will go on till the value of max new tokens, right? So which we will take as an input from the user, or we can also manually hard code that value, right? So this step of generation of new tokens has uh, two things, which is related to the max new tokens, till what point we will keep on generating the tokens, and the second thing is that we will only concentrate on the last token that is being generated. So we will get that logit, we will implement the softmax on top of those logits, we will convert those logits to the probabilities. So using the softmax, we will make sure that the probability distribution value will be in the range of 0 to 1. So once we get the probabilities, we will do the sampling using this torch dot multinomial. So then we will get the next index. So if you are not familiarized with this torch dot multinomial, I will request you to go back to the first video of this series where I have talked about what this torch dot multinomial is. And once we get that token, so what we'll do is we will concatenate that index next to the previously generated index, and then again we will keep on doing this loop, right? So we will pass the input, we will generate all the tokens, we will extract the last token, and that we will concatenate to the input, and that we will send again, right? So this process will till go on till we reach the max new token limit, right? So I hope now it is clear how the generate function is working. So using that, we will generate the output. So let's do that. So at first we will initialize the LLM and we will pass the vocab size. So once the LLM is initialized, then we will also initialize the tokenizer. Now we can send one input or a sequence with what we also can call it as prompt. So at first we will tokenize that prompt to get the context. So we will pass that context along with this max new tokens, which I am mentioning here equals to 100, and that we will pass to the LLM, and we will use this generate function to keep on generating the new tokens, right? So once the tokens are generated, then again we will use this tokenizer dot decode to get the final uh, textual representation of those tokens, right? So now as the LLM is not being trained so far, so we can see like random text are getting generated, and also the Shakespeare style implementation of the output is not being implemented. So in the next video we will try to do the full training of this LLM, and we will hope that the input token or the input text style will be captured by the LLM, and based on that more meaningful text will be generated, right? Already a long video. I hope you got all the concepts which are related to this LLM implementation. So with this I will end this video. Thank you for staying this long, and I will see you in the next video where we will do the pre-training phase of the LLM.